We're going to talk now about a different way to specify points in the XY plane. And just to get the idea started, I'm going to use two animations from the Wolfram Alpha Demonstrations website. I have the point 2, 1 shown on my grid, as close as I can get it to that. And when I use X and Y coordinates, 2, 1, we call those rectangular coordinates. Now, there's a different way that I can specify the location of that point, 2, 1. And that is by specifying the standard position angle whose terminal arm goes through my point and the distance of that point from 0. R is the distance from 0, in this case 2.23 units, and theta is our standard position angle in radians, 0.47. And so we can, instead of giving an x and y coordinate for the point, rectangular coordinates, we can give a radius and an angle, r, theta, to specify the location of the point. And r, theta are what we call polar coordinates. Here's another view of the relationship between polar and rectangular coordinates. This time I have the point 6, 3 rectangular coordinates, and I have the conversion into polar coordinates r, theta. In terms of how do you convert from one to the other, you'll notice that my distance of the point from 0 I can think of as the radius of a circle. And since we know the equation of a circle is x squared plus y squared equals r squared, we can come up with the value of the radius r. And in terms of the angle, which is here, the standard position angle, we can get that by using the tangent ratio. The tangent of my angle will have to be y over x. Just a couple more things with this. I'm just going to click on the rectangular grid. We're familiar with that. When we graph with polar coordinates, sometimes we use a grid that looks like this, which looks very confusing, but it just allows us to plot using the angle measure. And in this particular grid, these are all angles of 15 degrees, which would be pi over 12 radians, and then various circles indicating various radiuses that the point might be out. So let's just formalize this a bit. Just going back to our example of 6, 3 in terms of rectangular coordinates, that's the point here. In terms of polar coordinates, we need to find this angle and this radius. And we can think of the circle being like so. So as I said, the radius can be calculated by x squared plus y squared is radius squared. And root 9 times root 5, so 3 root 5, which is the number you saw in the animation. In terms of the angle, we know that the tangent of the angle will be y over x. And so theta will be the inverse tangent of 3 over 6, which, if you calculate that out, is 0.46 radians. And so we would say that the polar coordinate equivalent for 6, 3 in the form r, theta is the format for polar coordinates, would be a radius of 3 root 5 and an angle of 0.46. Let's just put exact notation down for that since we have that for the radius. Alright, so let's just plot a couple of points here. The point 1, pi over 4, r, theta. So we want to be 1 unit from the origin at an angle of pi over 4. I have a polar grid shown, and each of these is 15 degrees, pi over 12 radians. So pi over 4, 45, would be here, and a radius of 1 would be right there. That's point P. Next point, 2 units from the origin at an angle of pi. Well, I know that pi is over here, and so 2 units out is there, Q. Now, just while we're on this question, notice that we can talk about a negative radius. Negative r, theta is equivalent to r, theta plus pi. So in the case of this, we could label Q with a negative radius if we wanted to, and an angle of 0. So an angle of 0 would mean go in this direction for 2 units, but then the negative 2 would mean no, go in the complete opposite direction, 180, so over here. And so now here is an angle with a negative radius. We want to be 1 unit out, but we want to go in the opposite direction from pi over 2 radians. So positive pi over 2 would land us going in this direction, but we want to go 1 unit in the opposite direction because of the negative. And so our point is going to land at this location, R. So let's talk now a little bit more about converting between rectangular and polar coordinates. We did an example converting rectangular to polar, and we used these two formulas. If you want to go in the other direction, polar to rectangular, what we will do is take advantage of these two trig equations, right? We know that the x and y coordinates can be specified. The x as r times cos theta and y as r times sine theta. So converting these polar coordinates. All right, so let's just think these through. This is r comma theta, 2 units out with an angle of pi, which would be over here, and so 2 units out would land us there. Okay, in fact, we can see that the point rectangularly would be negative 2 comma 0. If we apply our formula, x equals r cos pi. Cos of pi is negative 1, so that's negative 2. Y equals 2 sine pi. Sine pi is 0, so that's 0. And so you can see that we get negative 2 comma 0. And the last one, the x-coordinate would be 1 times the cosine of pi over 4, which would be root 2 over 2. And the same would be for the y-coordinate. So the rectangular coordinates for r comma theta here are x comma y as so. So the next thing is to look at graphing equations in polar form. And equations usually come in the form r equals something involving theta. So we have an equation here, graph r equals 3, which means that the points we graph must have a radius of 3, be 3 units from the origin, and nothing is specified about theta in this case, which means we can graph the points for any angle that are 3 units away from the origin. So that would just be a circle with radius 3. And so this polar equation represents the circle with radius 3. Forgive my sloppiness on the tablet. It's a little hard to be steady. Now your calculator can graph in polar mode as well. So on your calculator, go to mode, and this time we're going over to the third setting, polar. And if you go to y equals, you'll notice that we have r isolated, and in this case r equals 3. And I graph, and there's my circle. Here's another question. We want to graph all the points with a standard position angle of pi over 6. Or another way to think of that is we want all points r comma theta. Now theta is specified. R is not specified, which means r can be any value. So you would probably think pi over 6, 30 degrees. I want all the points here. But you got to remember that r can be a negative value as well, which would bring us to all the points on the other side as well. And so the graph of this is a line. Let's now look at another equation. This one involves an r and a theta. So our equation is of the form r equals f of theta, or r of theta, however you want to say that. And so let's do a table of values, theta and r. So if my angle was 0, the cosine of 0 is 1 times 4 is 4. So I have a point that's 4 units out at a standard position angle of 0. That's there. And let's go every 45 degrees. So 45 degrees, cosine of 45 degrees would be 1 over root 2 times 4 would be 4 over root 2, which as a decimal is about 2.8. So a radius of 2.8 units out at an angle of pi over 4 would put me roughly there. Pi over 2 radians. Cosine of pi over 2 is 0 times 4 is 0. That would just be the point on the origin. 3 pi over 4. The cosine of 3 pi over 4 would be negative 1 over root 2 times 4 would be negative 4 over root 2. So that would be about negative 2.8. So now plotting this point, 3 pi over 4 as an angle in standard position is an angle going out this way. But since we have a negative r, we want to go this way. And we want to go this way 2.8 units. And so that would land me about there. And finally, let's pick pi radians. Cosine of pi is negative 1 times 4 is negative 4. And so instead of graphing towards pi this way, since it's a negative radius, we're going the opposite direction. And we can see that we're landing back where we started. And if we keep going, the pattern's going to repeat. So it looks like we have a circle here. Let's just go back to our calculator and check that out. Circle of radius 2. Now, let's work to convert this equation in polar form to rectangular or Cartesian form. So what I'm going to do is multiply both sides of this equation by r. And it may not be completely obvious why I'm doing that, but here's why I'm doing that. R cos theta we know is x. Right? X is r times cos theta. And r squared, from the equation of a circle, we know that that's x squared plus y squared. So x squared minus 4x plus y squared equals 0. And I mean, I can leave it like that, but let me just, what I'm going to do is complete the square to show you where the equation of the circle is coming from. X squared minus 4x, complete the square, take half of negative 4, which is negative 2 squared, so I add 4 to both sides. This factors x minus 2 squared plus y squared equals 4. And you'll recognize that we have the equation of a circle with radius 2 that's been shifted 2 units to the right. Here's another equation. This time it's given to us in rectangular or Cartesian form. And we're asked to sketch it and write it in polar form. To go from rectangular to polar, I need to reverse what I did in the last example. And that is to use the fact that x is r cosine theta. So make that replacement. And y is r sine theta. Square those out. I could factor out r squared. And you'll probably recognize that as an identity. That's cosine 2 theta, the double angle identity for cos. And if I want to isolate r squared, that would be 4 over cos 2 theta, which would be 4 secant 2 theta, square root, that's plus or minus 2 times the square root of secant 2 theta. So we'll have to enter this as two equations. It's having a little trouble going up here, but if you trace it, you'll see that it does. So as you can imagine, there's lots of different types of graphs you can get when you use polar equations. Feel free to experiment and try to create some interesting patterns. On the rest of the sheet here are some basic common types of graphs that come up, and you can finish those off. Try to rationalize in your head through what you think the graph would be by creating a table of values, either on paper or in your head, to get an idea of what it looks like and then confirm it with the calculator.